Thank you so much for having me. I'm Jing Zhang, an incoming faculty fellow at NYU Creole. My research asks how machine can reason about things that are broken, incomplete, or only partly observed. So today I want to start with a very simple puzzle. Suppose I give an AI system a pile of broken pieces like this. Can it recover the object that once formed? And here is a harder question. What if some of the pieces are missing? So I'll show you two pieces of my work, GARF and CRAG. We'll start from assembling what we can see and end with imagine the whole object behind what we see. Humans have always been curious about ourselves. Where do we come from? What are we? Gauguin painted these three questions onto a canvas more than a century ago. Paleoanthropologists and archaeologists ask very similar questions, but their answers are not written in the book. They are buried in the ground, bones, tools, pottery, and there is one problem. When we find them, they often look like this, broken. And this is true across different materials and across enormous spans of times. Different material tells different human stories. But when we dig them out, they often arrive in the same form, flakes, shards, or fragments. So in a very literal sense, the material record is a puzzle. And this is not a small puzzle. On the left is a tree of bone fragments from one excavation. On the right, pottery shards lying on the surface of a site. A single sealed season can produce thousands of pieces like this. Museums and archaeological collections are full of pieces waiting to be understood, and putting them back together by hand simply does not scale. So how difficult is this for people? Here you can see archaeologists manually refitting a vessel. They sort the pieces, compare the surfaces, try one collection, reject it, and try another. It can take hours, days, or much longer. So in one controlled lithic study, the success rate was only around 30%. So even for experts, reliable refitting remains extremely difficult. But why do we care so much about putting these pieces back together? Because assembly is not really the final goal. Interpretation is. And this is one site in France. Researchers found pieces of the same bone and stone tools that refit across different heads. So those physical connections tell us something much larger. The people around those heads or interacting with one another. So when you recover the refit, you can begin to recover the human story. And now let me turn this into a vision and a learning problem. The input here for our system is a set of scanned fragments. We represent each fragment as a point cloud. And initially, our piece can be a random position and orientation. And the job of the model is simply to describe for every fragment, predict where it should go and how it should rotate. So mathematically, that means one rigid body pose in SE3 for each fragment. And importantly, we only use geometry here, no label and no texture. So let's start with GARF. The idea for GARF is very simple. We want to learn from fake bricks and fix the real ones in the site. So here is the first problem. Machine learning systems need a lot of training data, but real broken objects are rare, difficult to collect, and expensive to scan. So almost all learning-based assembly methods depends on simulated fractures. A common benchmark is called breaking bad, with roughly 1 million simulated breakage examples across many different objects. And the simulation gave us scale, but it immediately creates another question. Will what we learn from fake breaks work on the real one in the site? So this become our first research question. Can model trained on simulated fractures generalize beyond its training world? We care about three kinds of generalization. The first is unseen object shapes. The second is new fracture patterns. And eventually, mostly real cases where some pieces may be missing or extra. So this experiment gave us the first clue. The previous data method called puzzle fusion plus worked quite well on everyday object distribution it was trained on. But we make one small change. Same fracture simulation, same assembly task. We only change the object category from everyday object to artifacts. And the part accuracy drops significantly. That suggests something important. The model learned a lot about the object shape, but not enough about the fracture geometry. So that led us to have our first key insight. If I show you one random piece of the pot, it may tell you very little about where it belongs. But if I show you its broken surface, that surface carries much more direct evidence about what it should connect to. So for assembly, instead of asking the encoder to mainly understand what object this is, we want it to understand where and how it broke. So the colored point clouds on the right are exactly the fracture regions predicted by our encoder. For local assembly, fractures as corresponding signals. So we gave the encoder one very simple pre-training task before the generation part. For every point, we predict is this point on a fracture surface or not. And this is nice because the supervision is basically free since we generate the synthetic fractures ourselves via the simulator. We already know which surface was created by the break. So this let us pre-train on 1.9 million fragments, about 14 times more than puzzle fusion plus. But the big win here comes from the pre-training task itself, not from the large data set. And another insight is more mathematical. So the translation is very easy to learn. If I move from here to here, I can follow a straight line. But the rotation is different. A rotation does not live in an ordinary Euclidean space. So if I treat rotation just like some vectors, the interpolation can be geometrically wrong. So instead, GARF perform flow matching directly on the space of rotation and the translation space. The translation moves along the straight line, the rotation moves along the shortest Walish rotation path. And the equation is on the slide, but the intuition is very simple. We just let the poles move in the geometry where poles actually live. And this is what the flow look like. We begin from almost random poles. We keep the largest fragment fixed as the anchor, then over 20 yellow steps, the other pieces gradually move and rotate into place. And we also notice something surprising at the inference time. The very first flow step already gets remarkable close to the answer. So instead of throwing that prediction away, we use it as a warm start and run the flow again from there. And one step along gives about 87% accuracy. Standard 20 step inference give about 94 accuracy. And even one plus 5 step can already outperform the normal 20-step flow matching. And there is another interesting observation. It is very practical in our setting up. This is not all every fragment carries the same amount of useful information. So the larger pieces usually have more stable geometry. Very tiny pieces can be ambiguous and can even destabilize the training. So instead of giving every fragment equal representation, we sample points roughly according to the surface area. Bigger fragments get more tokens and naturally receive more attention. So let's go back to our original question. Does fracture-aware learning actually generalize? We train assembly flow only on the everyday object and then test on the artifact category it never seen. We can see the visualization here. It performs very well. But it's not enough. We also ask, could synthetic to real generalization is also good? So we test our model on the fantastic breaks dataset zero shot. So where the real objects were physically broken and then scanned. So the result here is no fine tuning. The particle accuracy improves about 30 to 91. But we want to test this more systematically for the archaeologists and paleoanthropologists. So together with these experts, we built the Fractura dataset. It contains ceramics, bones, eggshells, and lasix. And importantly, these objects do not break in the same way. We include random breakage, incomplete ossification, and flank napping. And these are the real scan examples. On the left, you can see ceramic being reconstructed, and we also scan some bones. One interesting finding is we can scan only around 1 to 5 intact objects and simulate the break on it and train a small LoRa adapter based on our model. The test will be both states like this. But this is also where we discovered the limit of the GARF model. Lasix remain difficult because multiple flakes from the same core can have very similar geometry, and the performance drops when pieces are missing and when some unrelated pieces are added. So we ask the next question. What if assembly is not only about matching, but also generative influence? Can a 3D generative model actually help us put pieces back together, especially when the missing pieces are there? So our research question is, can model imagine the whole object in order to place the parts? And then once it can imagine the whole object, something new becomes possible. If a piece is missing, can the model also reconstruct a plausible version of what it should look like? So this sounds like a very learning idea, but humans already do this. When the expert reconstruct the skeleton, they do not look at two bone in complete isolation. They keep a hypothesis of what of the whole skeleton in their mind. Maybe this is one part from here. Maybe it should place here. So evidence from both pieces and the hypothesis about the whole. So we want the model to do the same thing at the same time. So this is the central idea of the CRAG. So the assembly and the generation should not be two independent tasks. They should help each other. The assembly branch tells the generation, here are the pieces, here is where they may belong. They give the generative model a part-level skeleton, and the generation branch tells the assembly, this is what the complete object should probably look like. So to make this work, we need to solve three problems. The first is the data. Our fracture dataset can teach the model about the broken pieces, but they are far too small to teach what every possible chair, vessel, bone, or object should look like when complete. So we do not try to learn everything from scratch. We borrow it from 3D foundation model. We reuse the SSG, a large image to 3D generative model pre-trained on around 2 million 3D objects as our prior for the complete shape. The second problem is the representation. The fragment branch and the whole shape branch need to communicate. But if they describe the geometry in completely different feature space, the communication is very difficult. So we let them speak the same language. We use the same YE to represent the complete shape and also encode each individual fragment. Now the fragment tokens and the shape tokens live in the same space. And the third problem is more delicate. We now have a very large pre-trained generative prior, around 1.4 million parameters. We want the assemble branch to talk to it. But we do not want the new signal to immediately destroy what the prior already knows. So at each layer, the two branches exchange information through the cross attention in both directions. We initialize output of this communication to 0 at the beginning of the training. Both branches behave almost exactly as they did before. Then they gradually learn how much to listen to each other. So this is the whole architecture. At the inference time, the two processes evolve together. One flow is denoising the fragment poses. The other is denoising the latent representation of the whole shape. They share the same time variables. So every step updates both assembly and the generation branch. And how do I teach the model to handle missing pieces? During the training, we randomly remove some fragments from the inputs, but the target shape is still complete. So the model repeatedly say partial evidence in, complete object out. So this is where compilation ability comes from. Now we can test the main hypothesis directly. Does imagination actually holds assembly? We can see the GARF on the larger dataset, part next. And then we add the share VE here. And then we add the image as a prompt. And then we add the generation branch. But this is much easier to understand visually. So here are some inputs fragments in the left, and here is the complete shape we generate. And here is the pose for each fragment we input. And now we remove some pieces. We import fragments that are not complete. And this is a situation GARF cannot fully reason about because some of matching evidence is simply gone. But the CRAG still plays out the pieces. But all the same time, the generation branch fills in the missing regions. And you might be wondering, is CRAG only able to do this because we give it a 2D reference image? The answer is no. In this example, 206 pieces are missing, and we provide no image at all. The fragment geometry alone is enough for the generation to produce a complete object. So the 2D image is useful, but it is not required. And the information also flows in another direction. Remember, we have two hands from a few slides ago. Sometimes the reference image is poor or ambiguous like this. If we use triple ST from the image alone, it fails to produce a valid mesh. But CRAG also has the fragment input. So with additional physical evidence, the failure rate dropped to 0 in these experiments. So generation helps 3D assembly, and assembly also helps generation. So of course, our real goal is not only to reconstruct the benchmark chairs. So we bring the model back to the scientific domain that motivated the work. Here are some real scanned ceramics and bones. We can say the generation and assembly result from our network. And we also show some failure case. CRAG does not solve everything. So some case is about the very thin shell. It may provide weak geometry constraint for the pose estimation, just like the eggshell. And another case is extremely slender structure can become thinner than the junction distance of the SDF. So opposite surface merge together. And open surface may be incorrectly closed because SDF is ambiguous as open boundary. So the reconstruction is biased towards watertight shapes. So let me step back and connect two parts of this talk. So the first part is GARF. It starts from the fragments. Given the fracture geometry, I can observe how do the pieces fit together and what are their poses. And CRAG at a different direction of the reasoning process. Given these incomplete observations, what complete object could help produce? And these two directions form a loop. The piece you say constrains the object you can imagine. What's the next step? So first, real archaeological collections may contain not 10 pieces, 20 pieces, but hundreds of thousands pieces. So at that scale, I do not think one network should solve everything in one forward pass. So we need an agentic assembly loop, form candidate groups, test them, verify them, and sometimes revise when an earlier decision was wrong. And the second step is we want better fracture simulation. So different materials fail in different way. Bone, stone, ceramics do not follow the same fracture process. So instead of random breakage, we want controllable material-aware fracture generation. And the third, we want human expert inside the whole loop. So the archaeological experts may have a skeleton, a textual hypothesis, or prior knowledge about the imagined object. So the model should be able to use this information and show alternative reconstructions rather than pretending there is only one answer. So finally, we need physics. At the end of the day, two pieces either physical fit as the same or they do not. So these directions came together in a broader program. We called it fragment lesson. from the archaeological sites to the fragments to the reface, and finally to the Hellman interpretations. So we start today with a pile of broken pieces. GARF asks how to put this wasteful evidence back together, and CRAG asks how imagination can help when the evidence is incomplete. And ultimately, the goal is not simply reconstruct one object, but to recover the human story behind it. Thank you very much. I'm happy to take questions.